In this video we're going to look about the ideas of diffraction of waves and how it affects telescopes. So diffraction itself is a fairly straightforward idea, but it has lots of implications. So if we think of a ray of light like that, which we've done for ray diagrams, that's one way of thinking about light. But we can also think of light as being a series of wave fronts. And so if you imagine that the lines I'm drawing now would be the peaks of waves that you would see. For example, if you saw waves heading towards a beach, you'd see the peaks of the waves. And the gap between each line is the wavelength. So two ways of representing waves. We can think of them as the line showing the direction, or we can think of them as a series of wave fronts. And the gap between the wave fronts is called the wavelength with the symbol lambda. Now, the wavelength is important in diffraction because the size of the wavelength affects the amount of diffraction that you get compared with what's happening with the gap it's passing through. So when you have a telescope, you have an aperture at the front. Whether it's a refracting telescope or a reflecting telescope, they both have an aperture, which is a hole at the front. Now when waves pass through apertures, they diffract. And what we mean by diffraction is spreading out. So here is a wave heading towards a gap, and so there's objects in the way. Now, diffraction happens as the wave passes through the gap and comes out the other side. And what you'll get is a tiny bit of curvature on the wave, and the wave will spread out somewhat. Now, the amount of spreading depends on two things. It depends on the size of the gap compared with the wavelength. If the wavelength is around about the same size as the gap, then you get a lot of diffraction. If the gap is much bigger than the wavelength, then you don't get so much. So if I do a few scenarios here, so if I have the same waves again, if they pass through a very small gap, which is comparable to the size of the wavelength, then we get an enormous amount of spreading out of the wave. Okay, so the gap is approximately equal to the wavelength. Then I get lots of diffraction. If the gap is large compared with the wavelength, then I don't get so much. And so the effect is sort of negligible. So if the gap is much bigger than the wavelength, then I get a little bit of diffraction. Now obviously diffraction is an unwanted thing in a telescope. You do not want your waves to come in to your telescope and then start spreading out, because they will interfere with each other and you can end up with all kinds of complications in your images. So for a telescope, the key for a telescope is that we want to make sure that the aperture, which is effectively the gap, we want the aperture to be way bigger than the wavelength of the light or the waves that are passing into it. And if that aperture is way bigger, then we don't have a problem with diffraction. If it's not, then diffraction becomes an issue. Now for an optical telescope, which uses visible light, the wavelengths are so tiny that it's not an issue. So optical telescope, the wavelengths might be, for example, I don't know, let's say 500 nanometers. So 500 times 10 to the minus 9 of a meter. So the wavelength is 500,000 millionths of a meter. So clearly any telescope is going to have an aperture that's way bigger than that. So in optical telescopes, diffraction is not a problem because the wavelength is so small. So diffraction, not a problem. But we also look at radio waves coming from space using a radio telescope. Now, a radio telescope, we have a problem because the wavelength could be meters, well, mainly centimeters, or meters, possibly. Now, if the wavelength is a few centimeters, then what that means is that the size of the aperture has got to be much, much bigger than that. And this is where it becomes a problem. So that the only way around avoiding diffraction in a radio telescope, where the wavelengths are much bigger, is you've got to make your radio telescope much, much larger. So that's why radio telescopes have to be very, very large indeed. So radio telescopes need to be big to avoid that kind of diffraction effect. Now, the biggest radio telescope in the world, I think, is around 500 meters in diameter. But obviously, those ones aren't very maneuverable. But you can get over this by using an array of telescopes. So you can use telescopes. So this is a series of radio telescopes arranged in an array. And you imagine that carrying on all directions. Then the effective aperture of the telescope, when you combine all of those images, becomes much larger. So these are individual radio telescopes. But if you arrange them in an array, in a big pattern, then you can make sure that the effective aperture is much bigger, and therefore you avoid diffraction. So diffraction, not a problem with an optical telescope, because that is a very small wavelength, and even a lens that big is millions of times bigger than that wavelength. With radio telescopes having wavelengths mainly in the few centimeters region, then even something that's a few meters is only 10 times bigger, say, than the wavelength. So you need to make sure your radio telescopes are as big as possible to avoid diffraction.